Our problem, in which we have hot air flowing with a mass flow rate of 0.05 kilograms per second through an uninsulated sheet metal duct of 0.15 meters in diameter. This metal duct is in the crawl space of a house. The hot air enters at 103 Celsius, and after 5 meters it cools down to 77 Celsius. The heat transfer coefficient, the H, between the duct and the ambient air is known to be 6, and the ambient air to infinity is 0 Celsius. We are to calculate the heat loss of the duct over the length of the L, of the length of the duct, which is L, so just simply Q, was Q, and determine the heat flux and the duct surface temperature at X equals L, assuming fully developed conditions. So this is very useful. So they want two things on this second part. They want Q, or simply put big uppercase Q over area, and also what is the temperature, surface temperature. So what do we have? Why is this question more complicated? Well, this question asks you to combine previous knowledge in a way that you haven't done so far. So we have air coming through, air is going. The direction, we know air is coming at 0.05 kilograms per second. We know it enters at 103 Celsius, and it leaves at 77 Celsius. Okay, we also know the T infinity being 0 Celsius. So beforehand, what we know will happen is we know Q is going to go from air to the outside, all right? And the other thing we know is that as my air is going through this X direction here, which we know will take 5 meters, 5 meters, it's 5 meters long, and it has a 0.15 diameter. We know that, the other thing we know is that our delta T is changing. If our delta T is changing, our Q is going to be changing, right? So note how when first we start, our delta T is 103, and then our delta T decreases as we go down the pipe, and by the end of it, our delta T is 77, right? 77 minus 0, 77 delta T. So if we were to draw our little, let's draw some magnitude arrows here for our Q, it would look something like this, right? It would be decreasing as we go down the pipe until finally it reaches, and then obviously my drawing didn't fit, so it would be like this, right? And it will decrease as we go further down the pipe, right? So we would have a decrease in Q as we're going down our X direction. Why is that important? Because to find the first part, part 1, that's pretty straightforward, right? Because we know the air is giving away energy. We know that we can calculate that energy by simply relating the mass flow, that's mass flow of air, it's Cp and delta T, all of which we have, and the only thing we don't have we can grab off the table. But to find out what is Q and what is the temperature, surface temperature of the duct at this point here, it's a bit more complicated, because then you have to find what's the Q, exactly the Q over here, and also find what is exactly the temperature there. Because likewise, like same way that our air is decreasing in temperature, so will be the surface of the duct as we go down this pipe, right? So that's the catch there. All right, so the first thing I'm going to do is let's find part 1, which is straightforward. We need to find what's Cp. We know that this air is going from 103 to 77, so we're going to grab properties of air between these two values, and I have table A5 down here. So between those two values, our T bulk, in this case here, will be the 77 plus 103, that is in Celsius. I'm going to go ahead and sum 273 to get it in Kelvin, which is 363 kelvins. And if that's the case, that's a horrible 6. Let me make that better. There you go. So if that's the case, then we're going to have to interpolate between 350 and 400. Okay, but the only thing I'm looking for at the moment is Cp, so I'm only going to grab Cp for now, so I'm only going to interpolate between these two guys here, and that is, what did I get? I got Cp to be at 363, that's Cp to be Where is it? 1.01. And that's kilojoules per kilograms Kelvin. Okay, so first part, very straightforward, no problems whatsoever. Sick and tired of doing that. We'll do mass flow rate of air 0.05 kilograms per second times Cp, that's 1.01 kilojoules kilograms per Kelvin, and our delta T is 103 minus 77 Kelvin or Celsius. So note that if I wanted to do final minus initial, it would be 77 minus 103, which would render a negative number, which would also be correct, right? But we know that energy is leaving from the start. We always knew that. So you might as well use positive numbers and just say you have a decrease in Q. Right, so we run these numbers. Let's just check units. Kilograms, kilograms, Kelvin, Kelvin. So that'll be kilojoules per second, which is kilowatts. And that is 1 point, whatever that is, 1 point, where's my calculation? 1.313 kilowatts. And that is answer 1. Okay, and the reason why this question is a bit harder in my opinion is because it can throw some of you guys off, right? Because what you would do in the past is, let's grab this number and use this Q to find the resistance, and with that resistance we can find the temperature we're looking for. So it'll be really straightforward, right? Or we can get this and divide by the area of the duct and get the flux, which would be incorrect, because they're not asking for the flux, the average flux throughout the whole pipe. They're asking for the flux at a specific point. Okay, so let's look at this analysis a bit more in depth now for part 2. What is going on? Let's think about it. We have 3 resistances, right? As our Q goes down the pipe, we have this one here, then we have one right on the pipe, and then another one there. So let's draw those resistances. We would have the one for air, then we have one right on the pipe, and then we have another one for the ambient, right? So from the first one, let's call this one R1. Let's actually do, these two here are convective resistances, right? Convective. And this here is a conductive resistance. So this one here will be our XKA, right? And this over here will be 1 over HA, right? So let me draw once again. Draw this once again. Let's give them some names. So I'm going to go ahead and call this one R1, this one R2, and this one R3. And you see why I did this in a moment. And the idea is that if we have them in series, then they're all going to have the same Q. However, as, like we mentioned before, right, as we go down the X direction, or the Q dx will be changing, right? The amount of energy that is, how can I say this? The amount of energy that is being released from the air into the ambient is changing as we go down the X path. So while the Q has to be the same in all 3 of them, and that's true, it will be changing. And the reason why it will be changing is because this guy will be changing, right? The resistance 1, if you guys recall, has that element there. And we know that the convective coefficient will be changing as we go down this pipe. Right? Now there's an approximation we can do. You can note that nothing has been said about the duct itself. The only thing we know is that we have this info here that is uninsulated sheet of metal. So that gives us a good indication that this let's put it this way, that R3 is way smaller than R1 and then R2. Okay, so much so that we can ignore it. So we can ignore this guy here, because it's very thin and it's very conductive, so its resistance is negligible in respect to the other 2. So this simplifies our problem, and then we're only left with 2 resistances. The resistance 1 and 2, and that's why I call them 1 and 2, right? 1 and 2. And what we're looking for is what is the Q that goes through these resistances. So what is the Q that goes through these resistances? Actually Q over 8, right? At X equals 5. And the other thing we're interested in is what is this temperature here, because we know there are nodes over here. We know this first down here we have 77, right, at X equals 5, and over here we have 0 Celsius. And we're interested in this temperature here, this T here that we don't know. That is the unknown to this problem. And this T here is unique to x equals 5. If we were to try to find this temperature at the beginning, it will be different because this value will be different and because this value will be different, right? So that's what we need to do. To be able to find this, we need to do, we can have a little, we can do our, what is it? Ohm's law, and Ohm's law tells us that the driving force will be the delta T over R. In this case, we have two R's, so we can do the sum of R's, and the sum of R's is R1 plus R2 plus R3, but this is approximately equal to R1 plus R2 because our R3 is very small, right? Like we said before. So long as I can find R1 and R2, then I can find my Q because I already have the delta T. And finding my Q, I can find the flux divided by the area, and I can also do the temperature that I'm looking for by relating either through this side here or through this side here. It should render exactly the same result if they're in series, right? Cool. And I can transform this into 1 over H area plus H area. They are different H's, so let's just call this 2 and this 1. The areas would be different if this guy was insulated or if this sheet was thick, but since nothing's said about it, we can probably assume the two areas are very similar. Okay, so this could be further simplified into 1 over area that multiplies. No, I can't do that. What I can do is 1 over area that multiplies 1 over H1 plus 1 over H2. Okay, so that's what we're going to be looking for because this has been given, and this is 6, and we've known this from the start. What we don't know is this guy here, and that's the issue, right? That's a hard thing to find. So let's go ahead and find that guy so we can solve this problem, finish this up. What do we need to do first? We need to find what is the condition. So Reynolds. In my Reynolds, I'm interested in Reynolds at x equals 5. So we'll need density, velocity, diameter, viscosity, and you've noticed we don't have velocity, so we can do that idea of the cross-sectional area and all that. So this will become 4 times my mass flow rate. You can check the previous problems we solved to see why this is, and this is going to be pi, diameter, viscosity, right? Same thing if it's a circular entrance. Now, there's one catch here before we move on, which is the following. Note that we're looking for Reynolds at x equals 5, right? Because that's the point in which we're interested in. So we're looking for a local Reynolds, a local Nusselt, and a local convective coefficient. So at this point in time, the properties that I need for this guy, actually this is the only property I want to plug in, and the properties that we'll need for Nusselt later and all that, will be the properties, not the bulk temperature properties, so not the 363 Kelvin properties, but instead the 77, right? 77 Celsius property, which is equivalent to 350 Kelvin. Okay, so I need to plug in the data for 350, right? And you'll see that 350 is, yeah, there you go. 350 is, we don't need to interpolate. So this is the properties I'll be using to calculate things now, from now on. Okay, so this will be 4 times 0.05. This is 0.15. This is pi. What is this guy here? This is 2075. This is 20,400. 20,000, yeah, 453. Okay, so our Reynolds is critical because Reynolds is greater than Reynolds critical, and if you recall, we're using 10K for that. So this guy is turbulent, and we have a situation in which we have turbulent flow plus, what was it, fully developed. So turbulent flow plus fully developed means we can use the approximation these lovely fellas here, and this guy is to the n, and then we need to determine whether this is 0.3 if it's cooling down, the fluid's cooling down, or 0.4 if it's heating up. And we're going from 103 down to 77, right? So therefore we discard this one and we keep the 0.3. Okay, so Nusselt equals, so plugging in our Reynolds at 20, where is it? Plugging in our Reynolds into there, and our Prandtl from 350, so the Prandtl will be 0.697. I got 57.985. We'll go ahead and approximate this to 58. Okay, which has to be in turn equal to the convective coefficient, the local one, times the diameter over k, and then this k again for 350, so this is 0.03003. So then when I calculate my h, I got 11.6, so 11.6 watts meters squared Kelvin. Okay, and this was the whole thing, right? The whole problem revolved around this, because once I have this, then things become straightforward. Remember that we have a knot here, then a resistance, then not resistance, and then a knot here. And on one side we have 77, so we have 77 over here. We have on the other side we have 0 Celsius, right? And don't forget that this is a snapshot, right? This, what we're looking at here, is a snapshot at x equals 5 meters, right? If we were at any other point, this would not be the same, this would not be the same, and this over here would not be the same. Okay, cool. We know that Q is going to flow this way, right? Q is going to flow this way, and we're interested in two things. We're interested in Q over A. We're also interested in this temperature here. Okay, so what we can do now is, okay, so if Q equals delta T over the sum of R's, because they are in series, we can sum these R's up, R1 plus R2. If we're interested in, let me just do a little trick here. Let me go ahead and divide both sides by the area. So I'll have delta T over here divided by the sum of R's and the area down here, okay? Then I can go straight into what I'm looking for. And this is 77 minus 0 on the top. And on the bottom, I'll have the area that is multiplying my sum of R's. And if you guys recall, the sum of R's is, let's do brackets, 1 over the area, 1 over H1 plus 1 over H2. Okay, so my little trick was so that I could get rid of these guys. And I just need to solve this math here. So that's going to be 77 on the top there. And the bottom will have 1 over 11.6 plus 1 over 6. And this renders 300 and approximately 304.6 watts per meter square. And I have Q over A. Right, so this is our Q over A, or also known as lowercase q, and that is one of the answers we were looking for. The other answer we're looking for is the T, right? We want to know what's that T in the middle there. And to find that, like I said, we have two options, right? We can go via this way, we can go via this way. What the hell, let's do both since we're here, just to make sure that we're doing the right thing. So the first one will be if we do delta T over R1, right? And then we don't have Q per se, what we have is Q over A, so we can again do the same trick with Q over A on both sides, but this will render that Q times R1 equals delta T, and this delta T is 77 minus the T we're looking for. There's no name for this, it's just called T star. Important to note that this one is going to be greater than this one, which in turn is greater than this one, right? So that's why I'm doing 77 minus T and not T minus 77. So this 304.6 times R1 R1 being whatever, 1 over 11.6, right? There you go. Has to be equal to 77 minus T star, so T star will be 77 plus whatever that thing renders, and that will be approximately 50.8. And that will be Celsius because we chose this guy to be Celsius. That guy will Kelvin. It will be Kelvin. Okay, so that will be the temperature in the middle there between the two extremes, so between hot air and the ambient air. So right on the duct, the temperature should be 50.8 Celsius. So let's just go the other way around. So this will be one way. Let's go the other way around. Just check, see, make sure that our math checks out. In this case, I'm doing with R2. So what we're doing is Q times R2 has to be equal to delta T. And in this case, the delta T will be 0, right? Oops, 0 is smaller. So T star minus 0. So this is an easier way to find things. What we're doing is 304.6. And R2 is just 1 over 6. Again, reminding that both Q, both this guy and this guy, that we're going to have one the area dividing, the other one the area multiplying, so the areas go away. And so we're just getting pretty much just 304.6 dividing that by 6, and that should render, that should give us the T star we're looking for. And indeed it does. Indeed, this is again approximately 50.8 degrees Celsius. So once again, we can be sure that what we did makes sense and that it works. If you have questions, hit me up.